Hello, I'd like to welcome you all to this lesson on the data memory. Now, you may all be aware that last time we started looking at the flash memory, in which we went into details trying to explain how a flash memory is actually organized. And we said that the flash memory is actually 32 kilobyte of space. And then we also mentioned that each component of a flash memory is actually divided into, the flash memory is actually divided into components or chunks of memory which are found at particular addresses. We also mentioned that the flash memory is divided into these components, and these components, these chunks of memory, are 2 bytes long, meaning that the flash memory is word addressable. Word means 2 bytes, and then we had to do some memory mapping, which actually gave us the picture of what we're talking about. In this lesson today, we are going to try to see another type of memory, which is called the data memory. Right. Now, if you try to look at the data memory itself and what it is composed of, it's not difficult to see that the data memory in Mega 32, because we mentioned that there are 2 types of memory. There's a memory for storing the code, and there's also the memory for storing data. Now, the memory for storing the code, in this case, which we have actually championed to be the flash, and the memory for storing data, in this case, is what we're going to refer to in this case, right? Now, how is memory for storing data organized in that Mega 32? So we do have what we call the general purpose registers. Now, the general purpose registers, the data memory is composed of 3 parts. So if we talk about data memory, then in this case, we're referring to these 3 parts. This is what we call the general purpose registers. Now, these are registers that are found within the Mega 32 CPU, as we would see later as well, and I gave you the general layout of these general purpose registers. We have got what we call special function registers, and then we've got the internal data RAM. But I want to mention here that if you talk about the general purpose registers, there are actually 32 in total, right? And we'll talk about memory mapping, and the special function registers in that Mega 32 are about 64, right? And the internal SRAM, or the static random access memory, is also part of the data memory, and it's about 2 kilobyte of space. Okay, please, I need you guys to note this. So this is what we have. So now the question that comes is that how do we do the memory mapping, right? So the first, in this data space, the first address to this somewhere here. So this, from here to there, we are referring to the general purpose registers, which are actually 31. Now, 32. So now, if you look at 32, we have to map them in their memory files, we can say that the first memory location is 0 in decimal, and the last memory location is actually 31 in decimal. But in hexadecimal, we can say that this is about 4 zeros, and the last memory location is about this, please, 001F. Right? That's in hexadecimal. Of course, 31 is what we have as a representation as the last memory location. So we do the cell mapping in the way you see it. All right. So in fact, if you check that these 4 zeros represents the 0, then the second one, which is the register number 1, sorry, is this. So this last number that you see right here is actually 31. I said there are 32 in total, but then we start counting from 0. So therefore, the last possible register that you get in the general purpose registers, is actually 31. The last possible register. Now, how are these registers packaged? Okay, what's the cell size? Well, the cell size of these registers is actually 8-bit, meaning that each cell is actually a byte long. So therefore, in terms of addressing the particular addresses, then we can start from 0 to R31, and each one is a byte long. So it's 8 bits long. So meaning that now the general purpose registers, since they are 32 in total, then therefore they start from, in fact, the other conventional name, about these registers, we call them R0, which is the register that is representing 00, to what? R31, right? So there's R0 to R31. Guys, we'll have a detailed discussion on these general purpose registers. But right now, we just want to appreciate how the memory mapping actually takes place. And they belong to the data registers, data memory. And the way they are stuck in this file, they come on top, and the first 000 belongs to the R0, the register number 0, and the last one belongs to register number 31. But then how long are they? They're about 8 bits long. Okay, so now let's make some progress. Now we can see here that if this number is really 31 here, right? And you can verify all of these, guys. Just get a calculator, convert the 31 to hexadecimal. That should give you 001F. Now, when we talk about the special function registers, now special function registers are also other types of registers that are found within the microcontroller. Now, these registers, they belong to like the input-output ports. They belong to things like the status register, we call it the SRAM, and we'll have a detailed discussion on this as well. We have special function registers such as the stack pointer high and the stack pointer low, and then we'll have a detailed discussion on this. Now, all these, if we package them, they are about 64 in total. Now, how do we now work with these registers, which is very important right here, guys. Now, we've mentioned that they are 64 in total, right? And where does the memory mapping start from? Well, if there are 64 in total, and we know that this is 31, so all we just need to do is to add 31 plus 64 to know what is the last possible memory location for this. So if we add 31, this gives about 95, right? So meaning that this right here that you see in this file, because immediately after this 31 we have 64, so we have to add 64 to get to the last possible memory address for the special function registers. Now if you convert this number, that number is equal to 95. Right now you can get to the calculator to calculate, but I want to show you also that after 31, then the next value that you get is actually 32. So if this number is 31, then in the hierarchy of addressing these cells, then the next number should be what? Should be 32. So 0, if you convert this to hexadecimal, if you convert this 00020, convert it to hexadecimal, convert it to decimal number, this is actually number what? 32. But since there's 64 in total, so we add 31 plus 64, we get about 95. So of course there are 32, but the last value is 31, and then there's 64 in total, so we just add. So the next address is 32, and the last address should be 95 within the special function registers. Okay, now we can see here that this is 32 and that is 95. So any address that ranges from 0020 to 005F belongs to the special function registers. And those are the ones that have been listed. Examples of the ones that have been listed. Let's just try to delete some of this stuff right here. Now, we have actually mentioned that there are 64 special function registers, and these special function registers are memory files. They're found in this space right here, stack pointer, for example, and these other timers, something, because there's quite a lot of them, and the special ones to pay attention are things like the input-output ports, and we have also the status registers. All right, these memory and locations, which are very, very much important, they're about 64 in total, and each one is found at a particular address, right? And we'll have a detailed discussion on some of them, especially the input-output ports. We'll explain in detail what TWBRI is and what TWSRI is. But right now, it's paying so much attention to the SPH and the SRAM, which are the very, very much important components which we'll talk about later on. All right. But right now, suffice to say that there are 64 in total, and the way we do the memory mapping is what I've just shown you. That, of course, we have this being 31, and if that being, and this is being 95. How did we get to 95? We just added 64. The other total, which is 64, we added, and they gave us the last possible figure, which is, and this 95 converted to hexadecimal, and that's what we get. Then we talk about the internal SRAM. Now we've mentioned that the internal SRAM is about 2 kilobytes. Now I want to mention that the SRAM is actually 2 bytes long. 2 is actually each cell for the SRAM is byte long. All right, and so if it's byte long, we know, and we've actually been talking about this, that the cell is the SRAM. If it's a byte long, then we know that memory size is actually measured in what? In bytes. And we know that 1024 bytes is equal to what? Is equal to 1 kilobyte. So for us to know what this address is, definitely you want to mention that if this is 95, then we know that 96 is actually 0060. It's not difficult to see because, I mean, if they're in a file, so the next number is definitely 96. Now from 96, what is the last possible memory location? And the way we get it, memory cell location, and the way we get it by trying to add trying to convert the kilobytes. So 10 to kilobyte, if you convert 2 kilobytes to bytes, that will be 24.8 bytes, right? Since these are not weight addressable, but they are just bytes, each cell is a byte long, then definitely we have about 2,448 spaces or cells, if you will. So the first cell, of course, since it's in a hierarchy, the first cell, the last one we had from the special function register was 95. So therefore, of these 2 kilobytes, we'll start from 96. Right, 96, right? But then since we are adding 95 to 2048 to find the last possible in this file, then we shall say 2048 divided by, plus 95, because the last one was 95. Then we shall have things like, okay, so this is what? This is 3. What else we have? This is 4, this is 1, and this is 2. So this is 2143. All right. Now, if you look at this, so we started counting at, we added, so this is 2143. And if we convert this number, since we add, so the last possible one should be 2143. If we convert this, that should be 2143. If you convert 0.85F, it should give you 2143, because now in this file we had 96, then 96 to about 2143. That's the last possible location that we have in this memory location. All right. Now we've mentioned that we had 95. Then from 95 we added 2 kilobytes. Now 2 kilobytes means that 248 bytes, and if we add, the last possible cell location is 8085F, and after 95 we get 96, right? And 96 is nothing but 000. So any memory that is ranging from 0060 to 085F, that memory is the SRAM. It's called the static random access memory. Okay, what is it used for? Well, the static random access memory is actually used for storing volatile data, right? We know that, guys, if you check in my video, if you check in this same PowerPoint, we have actually skipped some components which are very easy, just because those components will be very easy for you to understand and to pick. For example, what the ROM is, EEPROM, those are things you can just read and understand. And I just noticed that I skipped them because it's not a big deal. There's nothing so much technical. It's for you to just understand. But right now, we talk about the static random access memory, which is actually a memory that is used to store volatile data. Now, what do we mean by volatile data? Well, volatile data, this is just information that once that is that cannot be kept permanently in the microcontroller, meaning that when you switch off the data, when you switch off the microcontroller, the memory also, the data within that memory also gets erased. Now, when we talk about, so we've actually mentioned that this is how we do the memory addressing, and now you've seen how the memory addressing is done. But I want to mention here that we, in this data model, the data memory, we have, so we've mentioned here that there is a hierarchy of memory cells, and these hierarchy memory cells belong to the general purpose registers. That's those what we have. We have also the special function registers, and we also have the SRAM, right? But let me make a point here that these three are actually found in a hierarchy of cells, right? Like you have 31 of these, so therefore the cell location is 0, and then they continue in that hierarchy. Now, there is another type of memory location which is also stores data, but is not part of this hierarchy, and it's just on its own. And I want to take advantage to talk about this. You might meet it somewhere in the PowerPoint, but it's better we address as we talk about data memory. So, for example, we've mentioned that the SRAM is for storing volatile data, but there's also a memory location where you can store data permanently, and that is referred to the EEPROM, which is the electrical erasable programmable read-only memory. Okay, so now this EEPROM, which is the electrical erasable programmable read-only memory, is also part of the data storage. And apparently we've left it out in this hierarchy because it doesn't share the chronological order, if you will, in the way we are actually naming these cells. Okay, it's not part of this, it's independent. So, but I want to mention that it's mapped independently and it's on its own, and the way the way we talk about it, it's actually only 1 kilobyte of space. That is the memory size. All right. Now, if we talk about the memory size of 1 kilobyte, then it actually also means that we can also try to give the cell locations. So now, if we give the cell locations, what we mean, I mean, if it's 1 kilobyte, then it means that it's 1024 bytes long. And if it's 1024 bytes long, then the first cell location is going to be 000, right? Now, what should be the last cell location? So the last cell location, of course, you want to mention in decimal, it will be 1023, right? Now 1023, because you start counting from 0, so the last one will be 1023. So now 1023 is about 3 FFs, right? If you change it to hexadecimal. Now I just want to mention here that this sort of memory, it's on its own. It's like a flash memory, though it belongs to the data memory, and it's independent. Flash memory doesn't belong to this file of hierarchies where we have the general purpose register, special function register, and the static random access memory. The EEPROM also doesn't belong to this file, but it's part of the data memory. The flash is not part of the data memory. The flash is part of the program memory where we store code. All right, and I want you to take note that there's a EEPROM, and it's 1 kilobyte within that Mega32, and actually it follows the hierarchy where we see that the first cell memory is that, and the last cell memory is 1023. Okay, now I hope that, guys, that is very clear to all of you, and we're going to have also some detailed discussion on some of the stuff that we want to talk about. So now real quickly, let's just try to make some progress. You can't read quite. Now let's try to discuss the general purpose registers. General purpose registers. All right, now we mentioned here that part of the data memory is the general purpose registers. Now when you talk about the general purpose registers, we mentioned here that there are actually 32 in total, such that the first register is found in this cell location, and that first register belongs to the address 0000 or 0 or just 0 in decimal, and the last file register in this case is actually 31, right? And we know in this case we have what we call the ARA31, right? This is register number 31, and this address right here is ARA0, then the ARA31, but then the numbering, of course, is 0 to 31, and 31 we said it was 0, like 001F. That's what we said, right, in terms of the address. Now there are 31. Now there's some things that we need to take notice of these general purpose registers. Now, for example, guys, I want you to understand that the general purpose registers are the workhorse of the Mega32. This is where data is manipulated, and this is where data, when we begin to write the assembly language, you see that most of the times we use the general purpose registers to have access to the arithmetic logic unit, to do with access to memory locations such as the SRAM and the EEPROM. You'll see that the general purpose registers are actually used for data manipulations on every step of the way, and hence the need for us to really have an in-depth understanding of how these general purpose registers operate and how they are actually mapped. So the first thing that we need to discuss very quickly right here is the fact that the general purpose registers, of course, they range from ARA0 to ARA31. meaning that this is address 00000, and the last one being 001F, right? And we mentioned, but I also want to tell you this, that the general purpose registers, they are actually divided into two, right? And I want to mention this. The general purpose register from R0 to R25. These registers are packed as 8-bit long. Yeah, of course, the other ones as well are packed as 8-bit long, but there's a way they are called, and we'll talk about this. So we have R0 to R25. Now, if you talk about registers from R26 to R31, these, they are packed as 8-bit long, but they go as a pair of 16-bit long. So now what do I mean by that? If you see right here, for example, right? Let's just take right here. So this is a memory file R26, and R26 is 1A, and R27 is 1B. Of course, R26 is 8-bit long, and this is also 8-bit long. But these two, they go as a pair. They belong to the X register. They're called the R26 and R21. They belong to R26 and R27, sorry, they belong to the X. They are called the X registers. And to a level whereby, now what are we discussing right here, guys? What we're actually saying is that these are, though they are each 8-bit long, but they go as a pair. So we take them as a pair. For example, we can say that right here is R27. We take it as the most significant byte because it's 8-bit long. And this is R26, though they're in these files like this, but we take them that this is the most significant byte and this is the least significant byte. Now, here's the point. R27 belongs to the higher byte, and R26 belongs to the what? Lower byte. Now, what we mean by this R27, sometimes it's called the X high, XH. And R26 is called the what? The X low. But they are all together called as what? The X registers. Now, when you say X registers, it means that there is the X high and the X low. The X high, which refers to the register 27, and the X low being to the register 26. Now, also when you go to R28 and to R29, these are called what? The Y registers. To a level whereby R29 is actually the Y high, and R28 is the Y low. And if you can see also right here, we have the Z register. Now the R31 becomes the Z high, and R30 becomes the Z low. Now guys, I want to mention right here that these registers, the way they are packaged, though they are 8-bit long, but they can be referred to as a pair. Now, what are they used for? What's the big deal about them? Well, these are called pointers. Mainly, whenever you're accessing memory locations, you could actually see as we go on, like the flash memory, and these are that you find that we use these pointers to point to an address of a particular memory cell location. And now if you need pointers that can just point to an address, then we're saying from the general purpose registers, we have the XYZ, the XYZ instructions, also the XYZ registers, which are R26 to R31. These actually work as pointers. So what they simply do is to point to an address of a particular cell in memory and do some manipulations. Now guys, I'll show you the type of manipulations that are done with the XYZ, because these manipulations, the XYZ mainly are used in a type of addressing which we call the indirect addressing. Now, indirect addressing and direct addressing are part of these lessons, and we're gonna have a detailed discussion of how what we mean by indirect addressing or direct addressing, because addressing modes has to do with how we handle the data that is found in particular memory locations. How do we manipulate them? So the way we manipulate them either by directly working with the data or indirectly working with the data. And apparently this special type of field has got a special naming in microcontrollers. It's called the addressing modes. And the XYZ are normally used for indirect addressing. So this is what we use them for. But we'll have a detailed discussion as well on that one. But right now, suffice to say that there are 32 GPO registers, general purpose registers, and these range from R0 to R31, and they're used as accumulators for most math and logic. Like I mentioned, that the arithmetic logic unit for manipulations and things like that. And the XYZ are 16-bit registers and overlap. Now, this is very important right here. Now, we did mention that R26 alone independently is 8-bit, and R27 alone is what? Is also 8-bit. But these, they go as a pair. When they pair, they become 16-bit registers, but they become as 16-bit long registers, and you refer to them as the X. And if you just want to make use of just one type of, let's say, R26, then you can talk to it. You can talk to it as an X low, and if you want to talk to R27 alone as an X edge. But normally they go as pairs. And very important to digest this information, people. Okay, and again, they are used as what? Address pointers. Okay, or to contain large values, and then they can store large values. Of course, if they are going as a pair, then definitely they can specify values that is larger than 255. Now, where is this 255 coming from? Because we know that each byte they are 8-bit long. So because it's 8-bit long, then we know therefore that we can specify these locations up to a maximum of about 256. But because we start counting from 0, so we can specify from 0 to 255. But should we want to have more storage of data or something like that, or should we want to point to specific addresses? Most of these addresses, you find that, like the flash memory, for example, you see that it's 8-bit, 16-bit long, and we may just need to address them by our pointers as well. But I want to mention that pointers, mainly you see them being used whenever we want to access data from, let's say, any memory file in memory, like the SRAM, let's say at address number 0060, the one we just saw, which was 96, or maybe address number 0085F, the last one in the SRAM. You see that mainly the pointers, the XYZ, are actually used to access the data, right? Now, we can just try to look at the special purpose registers, and when we can try to real quickly look at some of the ATmega32 register models so that you are able to appreciate the register models of the ATmega32. Now, I want to mention here, if you look at, for example, if we take a look at the model of registers that are found, basically you need to really appreciate in general how we put these things. Okay, so for example, right here, for example, here we have the general purpose registers, right? Now, general purpose registers, we mentioned these are registers that are ranging from R0 to R31, and they're 32 in total in nature, and each one of them independently is 8-bit, and the function is to store data, right? We have the address pointers. Now, the address pointers are the ones that I mentioned, that from R26 to R27 to R31, they are called the XYZ, all right? And there are 3 of them, right? And we can, if we refer to them as pairs, then they are 16-bit long. and their function is to store address pointer. They point to an address. We have a type of register as well, which is called the stack pointer, and stack pointer belongs to the special function registers. And I want to mention here there's going to be a detailed discussion on stack pointers as well, because they're important, and they are actually 16-bit long. The size is what? 16-bit. Now, how are they 16-bit? Because when we are mentioning them, again, because when just like the XYZ, there's the stack pointer high, and there's the stack pointer what? Stack pointer low. You will see this as well. While this is 8-bit, and that is 8-bit, but when they go as a pair, they are 16-bit long. And stack pointers store a pointer to a group of data known as the stack. Now there is going to be a detailed discussion as well. Now there's a program counter which you've seen us talk about. We've been talking about the program counter every step of the way, and we say that the function of the program counter is to point to the address of the next instruction to be performed. All right. Now, program counters, they contain the address of the next instruction to be performed, but I want to mention right here, guys, the program counters are actually, in this case, they are 14-bit long. Right? In the arithmetic 2, program counter is actually 14-bit long. Now, why 14-bit? We'll have a detailed discussion. But right now, they're just 14-bit long. Just keep it in your mind that the program counter is 14-bit long, and there is actually a significant reason for that. And I want to give you just your own homework. Can you go and check why should we have a 14-bit long in the? What's the rationale behind it? There is a rationale. I want you to go and get it. Okay, now there is what we call the status registers. The status registers, the SRAM, we have one status register, and then we have one status register, right? And that status register is actually 8-bit long, and I want to mention that the status registers belong to the special function registers. And what do they contain? Well, they contain information on the results of the last instruction. They contain information. Now, what that information is, we'll have a detailed discussion, and I'll show you by a practical example. But right now, let's just try to look at also this model, the AVR CPU model. It's not difficult to see that we have what we call the stack pointer, just the one that we've mentioned. And I want to mention that if maybe, let's say, for example, if we look at the program counter itself, so we can see that the program counter is actually connected to every bit of this. All right, it's connected to the SRAM right here. It's connected to also the general purpose registers, and the reason for all of this, we know, is to point to memory locations, the next instruction that needs to be performed. Therefore, it needs to have a hand and a pointing to whether we are working with the SRAM, it needs to point to that. If at a particular point we are working with the addresses that are coming from the general purpose registers like the R0 or R31, it actually helps us to point to that as well. And now we can also see here that the arithmetic logic unit, whenever it does its computation, it has to be connected also to the status registers. Now, for simple reasons that the status registers, it holds also information related to whatever results of the manipulation that should be. And I'll show you the content of how this register looks like. But right now, suffice to say that whenever the arithmetic unit, also when you look at the arithmetic unit as well, it's very important to understand that whatever manipulation the arithmetic unit does, it's actually getting information directly from the general purpose registers, because these are the workhorse of the manipulations. Now, we can see from here that there is the also, like I've mentioned, the status registers, and from there, whenever manipulation has been done, the data could actually be sent through the data bus, which is right here. And the data that is sent it doesn't come directly to the arithmetic logic unit, the SRAM can actually the arithmetic logic unit can pass the data to the data bus to affect the SRAM, and the SRAM also can talk to the arithmetic the general purpose registers. All right, now things like the stack pointer, of course, there could be exchange of data between the data bus. It can receive data from the data bus, and it can also send data to the data bus to finally go to the SRAM, or to finally go to the status registers, or to finally go to the SRAM, and finally from the SRAM we can pick that information out to the arithmetic logic unit. Now guys, you will see, if you find that, you'll see that the link between the general purpose registers and the arithmetic logic unit is mainly the link that is used for manipulations of data. All right, you'll find that I cannot go directly to work these manipulations without going through the general purpose registers, and we'll have a detailed discussion. But right now, suffice to say that we do have the program counter as well, the function we've mentioned before, the stack pointer, we've already talked about it, and the program flash. This is where, of course, we know this is where we store the code for programming, right? We have mentioned that this is where we do the program. This is where the program is actually held, and then from the program flash, of course, we do have the instruction registers. Now we've mentioned what this instruction register is before. Now we did mention that once the program counter points to the address, then the data is actually sent. Then the instruction register actually holds the binary code of a particular instruction that needs to be performed. And now once that instruction has been held, then definitely the instruction decoder instruction control unit would actually make out what that instruction is and actually pass it on, right? All right, so not a big deal, guys, about all this. The most important thing is that you really have an insight of what types of things are found within the ATmega32 model or register model. These are some of the registers that we have within this microcontroller. Okay, now so that I don't make this video too long, I would like to end right here, and the next time we'll talk about the memory mapping. We've already talked about it, and I'll just try to explain in detail what this part is all about. I'd like to thank you for viewing, guys, and I'll see you in the next class.